Okay guys, in the last couple of videos you've been talking about alpha decay and beta decay. Just a quick reminder, alpha decay is this particle. Basically there's a part of the nucleus that is going to break off and shoot off. Okay, and so basically you learned in alpha decay that when you take those particles out of the nucleus and you throw it away, the nucleus isn't the same anymore. It had 92 protons, now it lost 2, so it's down to 90. Okay, and 238 loses 4 total particles, so that's going to be 234, and that's thorium on the periodic table. How do I know? Because element 90 is thorium. Is that radioactive? Yeah, because it's above 84 on the periodic table. Okay, so anything that's 84 and above on the periodic table is automatically radioactive. Okay, so that could go through another alpha decay, could go through some other steps. Beta decay, on the other hand, slightly different. It's 0, -1 beta. Okay, and in a beta decay, it's really a high-speed electron that's shooting off. Now, basically, in this first one, you could always check your math. 234 plus 4 is 238. 90 plus 2 is 92. You can do the same thing here. Top number is going to be a 14. Okay? Because 14 plus 0 is 14. This one's a little bit tricky if you remember from the last video. This is going to be a 7. 7 minus 1 is 6. So it ends up becoming a nitrogen atom. Okay? And I would have to tell you if that one's radioactive or not. If it's above 84, automatically it's going to be radioactive. But if there are other versions of things that are radioactive that aren't 84, and it's an isotope. So this isn't normal carbon. Carbon is 12 and 6. This is a radioactive isotope. Are all isotopes radioactive? No, but some of them are. It's like saying all dogs are chihuahuas. That's not true, but all chihuahuas are dogs. Okay, so you got to get that statement right. All isotopes are heavier or lighter versions of an element, but are they all radioactive? No, they're not. Okay, so this is alpha decay and this is beta decay. There's also another one that happens sometimes called neutron decay. And neutron decay, let's take this 23892. Make sure you write this one down. Neutron decay looks like this. 1, 0, neutron. So basically it's a neutron shooting off. Okay? Doing the math very simply, just to check our numbers, what number does that have to be? That 237 plus 1 equals 238, so that's 237. And what number plus 0 is 92? Well, if you look at the periodic table, uranium is 92. So what really happens in a neutron decay? It's the same element. It didn't change. See, in this one, the element changed because I went from 92 protons to 90. In this one, I went from 6 protons to 7 protons, so the element's changing. In this case, it didn't. Why? A neutron decay is just a changing of mass. It just got lighter. It went on a diet. Well, not really, but it lost a neutron. And so that neutron's shooting off. So these are particles that shoot off. Now, all 3 of these fall into a category called fission. Fission. Fission is when you're going to take an atom and you're going to break it into smaller parts. Okay, we already said that this is still reactive, so radioactive, it could go through alpha decay, but how do we know these things are happening? You watched the video with this guy named Becquerel that discovered it. How do we actually know? Because can we see these particles? No, we can't see the alpha or beta or neutron particles, okay, but there are devices that we have. Here's one that we happen to have at school. This is called a Geiger counter. Now, this is a handheld Geiger counter. Sometimes you'll see in movies where they'll have something radioactive. You'll see guys with headphones walking along, beep, 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 beep. It looks like a metal detector, but in that case, it's looking for radioactive material. So if I turn this thing on, I'm going to get it close. You can see the scale. Hear it click. It might pick up a few particles. But what happens when a Geiger counter is really around something that's radioactive? It's going to sound like this. We'll get a little closer for you so you can hear it. I have something radioactive, and it's actually this substance right here. Now, if you look at it, it's a plate. That's a special kind of plate, okay? Now, it's a plate like you would eat off of, okay? But they don't make this anymore, okay? Now, if you know anything about pottery, and I'll prove to you. Look at the scale. Boy, it's going crazy. This is giving all kinds of radioactivity off. Is it a lot? No. If it was giving off a lot, then the scale would be topped out at the very top and it wouldn't even sound like clicking. It'd be a constant sound. But what is this? Okay, when they make pottery, if you go back a long time, centuries ago, they used soil, they used mud, and they would shape it and then they would heat it, okay, and you would make plates. Okay, as a matter of fact, if you've ever seen ceramic ware, that's what they do. If you've ever had a mug that you wrote on and then they heated it so that all the writing stayed on it, okay, that kind of thing. Well, this plate is a company called Fiestaware. And just this color, if you've ever been in Colorado or New Mexico, you've seen that the soil is this color in the mountains. You'll see bands of this color. Well, this kind of soil has more radioactive uranium in it than our soil does. Okay, so there's elements found in the soil all the time. Gold is found in certain parts of the world more than it is here. Silver, all kinds of elements. Sulfur, if you go to Sulphur Springs, Texas, there's a lot of sulfur in the ground. And so as you drive through there, you smell it because sulfur smells like rotten eggs. Okay, so in the parts of New Mexico and Colorado, when they were making Fiestaware like in the 40s and 50s, they wanted this bright orange color, so they would use that soil, but they didn't know it was radioactive. Now, a couple of things for you to know. If I put something on here, we watch videos and watch movies, and we think radioactivity does things that it really doesn't do. So if I rub it on me, okay, then I'm going to put it away from me. Let's see if it transfers radioactive. It doesn't transfer radioactivity to me, so it doesn't rub off. So we watch these movies like the Hulk and things like that. It doesn't rub off like that. Okay, now, what I would not do is I would not eat some of this, ingest it into my body would be a real problem. Okay, so I'm just around in a couple of minutes just to show you how it works. Okay, but these clicks that you hear are these particles that are coming off, these alpha particles and beta particles. And they can be used for a lot of different things. We've learned how to use them in medicine to do some really cool things. We've learned how to look inside the human body without having to cut somebody open and look inside. If you ever known somebody that had to have an upper GI, which is your gastrointestinal tract, they're having esophagus problems or stomach problems, maybe they have ulcers, you'll go to the doctor and you drink a radioactive barium solution. Okay, it's an isotope of barium that's radioactive, and you drink it and you go sit in the lobby for 10 or 15 minutes, and then you come in, you stand in front of a screen, and they take a picture. And when they look inside, they can now see everything inside. They can see if there's a problem. They can see if there's ulcers. Ulcers are very, very painful. Okay, and they can look and see what's going on. If it's in your lower GI, your lower stomach, then they'll have you drink that and go sit in there for about 45 minutes. So it goes down your system, and it basically, the radioactivity makes it light up on the screen. So when they take a picture of it, it's like an x-ray, they can see everything. Now, an x-ray sees bones. When you take an x-ray, it goes right through your body and only sees the hardest, most dense parts of your body, which are going to be your bones. But you can't see all the organs. But when you drink something like that, it lights up on the screen. You can take a picture, and so they can see what's wrong, so they have an idea what kind of surgery you might need. And there's lots of different things that go on, or sometimes they look and go, nope, there's nothing there. Okay, so we've learned how to use radioactivity for some really cool things like medicine. Okay, a friend of mine that used to work at Richland a long time ago, she had your thyroid is back behind your throat right here. So when I poke here, it makes my voice change. But your thyroid is back behind here, and she was getting really sick, and they thought something was wrong with her thyroid. Okay, your thyroid gland, which is way back up in there, back behind your esophagus, is where a lot of your hormones are given off, so it makes you stay steady all day long. Okay, and so when you have normal sleep patterns and how all of the chemistry of your body works, a lot of it's going to deal with your thyroid. And she was getting really sick, and so when she went to the doctor, they said, we think you might have a thyroid problem. Now, there's one place in your whole body that takes iodine. Now, we eat iodized salt. And so they took radioactive iodine, and that's your thyroid gland. That's where they can see it, and they injected her with it. And so about 20 minutes later, only place that picks up iodine is right here. So they took a picture of her neck, and she had cancer. And so they were able to go in and do surgery and cut off all the cancer. And so she doesn't have thyroid cancer anymore. But every year she goes in to check to make sure it hasn't grown back. Okay? Now, if you take your part of your thyroid out, the hormones that you would normally make, your body doesn't make. So all she does is take different types of pills that keep her body and all the chemistry of her body working right. It's awesome. And so one day she was at school and she just looked really, really tired. Like, oh my gosh. I'm like, what's wrong, Leslie? And she said, I just don't feel very good. They've taken me off my medicine because it's now time to take an x-ray and see if the cancer's come back. And so when they inject her with radioactive material, they took a picture of it and it hadn't come back. And so they were able to give her medicine. She's back to normal after the weekend. Now, what's really interesting about that is when you have that kind of medicine in you, you're radioactive for about 24 hours until your body washes it all out of you. So you can't be around really small children. She had a young child that was about 5 years old at that time. And so the grandparents had to keep him because it's not safe for him to, she's slightly radioactive. I had the same kind of test done. I did what they call a nuclear test. And so they were checking out, my family has a problem with heart issues. And so at my age, you start looking to see, hey, how is your heart? How are your organs looking? And I had the same thing. I had the nuclear test, and they did that, and they took x-rays, and everything was perfectly fine, very good. They didn't have to cut me open and look. They could see inside. So we've learned how to take these processes that are fission and use them in medicine. Now, we've also learned how to use them in really bad ways as well. If you take a radioactive substance like uranium and you collect a whole lot of it on the end of a bomb and you drop it out of a plane, when it hits the ground really hard, this is what happens. Now, this is natural. Okay, so I was showing you with this plate. This is the natural process. I'm not making it happen. I'm not making that happen. It's just happening by itself. But if you had a sample, let me explain real quick. Let's say we only had this much uranium in a cube. Pure uranium. That might be trillions upon trillions upon trillions upon trillions of atoms. And when it sits there, it just normally goes through alpha and beta decay, which is fine. When you drop it out on the end of a bomb and it hits the ground and you make all those trillions of atoms give off these particles, something crazy happens. Here's the part I hadn't taught you yet. When this goes through alpha decay, it makes this plus some energy. Aha, I did tell you that. What is that called? Gamma, right? When this goes through this, you have a little bit of gamma made here too. You have a little bit of gamma here. Now, normal process. So when I touch that plate's not hot. Okay, it gives off so little energy. But when you drop it out of a plane and it hits it as a bomb and all these trillions of atoms all break at one time, you don't have a little energy. You have a tremendous amount of energy. When they dropped the bomb on Hiroshima in World War II, anybody that was standing outside within a quarter mile of when it hit, it was so hot, it was the temperature of the sun for a half a second. Anybody that was standing outside was cremated immediately. They were gone. They were dust. Their clothes were gone. They were gone. Trees were gone. It was so hot. Okay? And so when you cause this reaction to happen in a great amount of energy, it can do massive damage. People that were 3/4 of a mile or further away, there were stories of people that were outside reading their newspaper and their newspaper just caught on fire. The temperature of the air got so hot, or their clothes caught on fire. Why? Because the air got so hot for that split second, anything that was flammable just caught on fire. So it can get out of control. They use this in nuclear power plants also, in a controlled atmosphere. They'll have radioactive uranium or another radioactive element, and they'll shoot these particles in and start this reaction, because when you make energy, you can make electricity. We've learned how to do that. There's a nuclear power plant just an hour from here in Glen Rose, Texas. It produces all the electricity for that whole county. As long as you keep it under control, it works great. Now, you've probably heard of Chernobyl. Chernobyl nuclear power plant in Russia. Many years ago, this process was happening, and they would do it to produce electricity. It worked great, and then it got out of control. It got so hot that they couldn't cool it off, and it got to the temperature of the sun. Blew up the top of the building, just blew radioactive material all out into the air. And for miles and miles, this radioactive material will fall to the ground. All of the grass would be radioactive. All the animals would be radioactive. People that it got on them, if it didn't kill them immediately, they would have radioactive sickness where they'd be throwing up for a long time if it didn't kill them. People that survived it, as they would grow up and they would have children, their children would have massive birth defects because of being around nuclear reactive particles for a long period. And it didn't happen for very long. And so it can be very, very dangerous. Now, we don't dig in our backyard and find uranium, not in that amount, okay? Not in that amount at all. It's when we as humans have put a lot of it in one place and tried to do destructive things with it, okay? So a nuclear power plant can work really good. We also learned just a few minutes ago it can be used in medicine. All of those are called fission reactions. The other reaction that I want to show you real quick is the opposite. And it's called a fusion reaction. And you know the word fuse? Fuse means to take two things and put them together. Okay, and they stick. Okay, so here is an example. This is what happens on the sun. On the sun, you have hydrogen gas under really, really extreme pressure. And under extreme pressure, it pushes those atoms until they stick together. And when they stick together, when you get two protons on the bottom, that is helium. you make helium atoms, and then what you make is a tremendous amount of energy. When that energy is made, this is what keeps us alive. You've learned that if the sun goes out, we're not going to live much longer. Okay, we're just not. The energy of the sun is the beginning of all the energy on the earth, isn't it? And it comes from a fusion reaction. Notice in fission reactions, you take something and you break parts off. This is a natural process. Fusion, natural process on the sun. You take two parts and they stick together. You make something else, and they both of them give off energy. Now, we can't make this happen on Earth right now. If we could make fusion happen on Earth in a controlled situation, we'd have an endless amount of energy. We wouldn't have to worry about gasoline, coal, and oil, and wood, and all those things that we're starting to run out of, and we're worried that down the road we're going to run out of those things. If you had fusion, you could actually have an endless amount of energy. The problem is the Earth has an atmosphere on it, and because of the air pressure that's on us all the time, we can't, even in a laboratory, get this to happen, to make fusion. We just don't get it to happen. Okay, this happens on the sun. Okay, fission reactions, fusion reactions. We've learned how to use them for really, really cool things in medicine, and maybe some not so cool things when it comes to war, or maybe a nuclear power plant that gets out of control. And just Chernobyl was a long time ago, but about 4 years ago, in Japan, their nuclear power plant got out of control, and it's been pumping nuclear waste that's just ruining their water supply. So we were learning that science can be used to do some really cool things. Okay, fission, fusion, alpha decay, beta decay, gamma decay, and even neutron decay that we did a while ago. All right, you're going to do some practice problems with each of these.